Welcome back. Today we're going to look at acids and bases.
Acids and bases are everywhere. They're used to make foods, soaps and detergents, fertilizers, explosives, dyes, plastics, pesticides, even paper. Our stomachs are very acidic, our blood is slightly basic. Our proteins are made up of amino acids, and the letters in our genetic code, those A's, T's, C's, and G's, are all bases. You were probably taught how acids and bases behave on the molecular level. You were probably never taught that a long time ago, like ancient Greek ago, before anyone knew about atoms or molecules, acids and bases were defined by how they behaved. Acids tasted sour and corroded metals. Bases felt slippery and could somehow counteract acids. When molecules dissolved in water interact, they're exchanging two main currencies with their surroundings: protons, also known as hydrogen ions, and electrons. Depending on how a molecule is composed or shaped, it may be willing to donate or accept either protons or electrons with some other community member. And some molecules are far more aggressive than others when it comes to donating or accepting either currency. Remember that protons are positively charged and electrons are negatively charged. So if a molecule is willing to give up a proton, that's not too different from it being willing to accept an electron. Either way, it's becoming more negatively charged. Other molecules are willing to accept a proton or give up an electron. These are becoming more positively charged. Some substances are so aggressive about donating their protons that when they get a chance, all of the molecules in a sample will dump a proton, sometimes more than one, to the surrounding water molecules. We call these strong acids. Meanwhile, some compounds are so ready to accept a proton that they won't wait around. They'll just rip one off water, which usually has two protons but is generous enough to hang out with just one. We call these strong bases. Other acids and bases are not so strong. They may donate just a few of their protons to water, or accept just a few protons from water, but most of their molecules stay exactly the same. If left alone in water, they'll reach some equilibrium point, where maybe only 1 out of 100 or 1 out of 10,000 of their molecules has exchanged currency with water. As you might guess, we label these acids and bases weak, but in the common sense of the word, they're not weak. The vinegar in your salad dressing that you can smell from across the room, that is a weak acid. The ammonia you spray on glass for a streak-free shine, that is a weak base. So it doesn't take much to be an active player in the chemical economy. Most acid-base chemistry takes place in water, which can act as either an acid or a base, accepting deposits and enabling withdrawals like a 24-hour molecular ATM. And when a proton deposit customer, that's an acid, and a proton withdrawal customer, the base, shop at the same time, their net effects on water's account may cancel out, and we call this neutralization. Now, certain molecules can behave as acids or bases without water, but that's another story. Let's end by saluting water as the resilient and fair banker for acids and bases. It's always open for business, doesn't charge interest, and will never foreclose on your molecules. Which is more than I can say for wah wah.
Alright, so acids. Common substances used in a wide variety of things in everyday life. Some of them are potentially dangerous, so even we talked about last lesson in the indicators and pH, the stomach acid that your body contains itself is so acidic that it's actually very dangerous if it's not in your stomach. So it can eat away metal, wood, clothing, and it can burn your skin on contact. So we have to be really careful with these things. For example, battery acid contains sulfuric acid, which is very strong. It will burn your skin. So in this case, we're talking more about your, like a car battery style, contains liquid sulfuric acid in it. Your typical battery, like is shown here, is often sealed. So it will contain an acid, but it's very difficult for it to get out. Sometimes you see, if you leave a battery lying around for a long time, you get that sort of like crusty surface that builds up on it. That's actually a slight leaking of the battery, and it's corroding the surface, leaving that crusty residue. So what are the properties of acids? They have a few key important properties. First, they have a pH less than 7 that we saw last lesson. Secondly, they are corrosive. They have a sour taste. So they taste sour if you eat them. And obviously, I'm not encouraging that to be the testing method. Don't go around eating acids to see how strong they are. But at the safe levels that we use in food, they have a sour taste. And they are particularly reactive with metals. And we'll see in a later lesson what those actual reactions are and what is produced from a chemical equation perspective. They're also neutralized by bases. So some of the key properties. Let's look at examples. Yogurt contains acid. It contains lactic acid. Your soft drinks are actually quite acidic. And you've maybe heard about that. A Coke is really bad for you. It's very acidic. It dissolves your teeth, etc. It contains carbonic acid. Lemons are a citric acid, which other fruits do contain as well, but it's citric acid. Vinegar is acetic acid. Rhubarb leaves actually contain oxalic acid. And grapes actually are acidic as well, and they contain tartaric acid. So again, lots and lots of different acids, just some places that you would see it in common foods. And this is what gives it that taste we're talking about. So let's have a look. A list of some common acids and their pHs. So we've got hydrochloric at the most strong, the strongest. So pure hydrochloric has a pH of 0. It's extremely strong. This is the one that we'll see can digest fluid in your stomach. We use it for metal cleaning and pickling. Sulfuric acid we use in batteries, fertilizer, oil refining. That's a pH on average 0.3. So again, we are talking the concentrated versions. Sometimes you'll look online and these numbers will change. Really depends on how concentrated they are, how pure that acid is. Nitric is used in fertilizer, rocket fuel, and etching materials. That's a pH of 1. Acetic we saw before in vinegar, still pretty acidic. Pure acetic acid is a 2.4. Citric going down, that's the one we see in our fruits and lemons, 2.2. Remember, lemon has that really distinct taste. It's because of the acid that it tastes that way. Carbonic, our soft drink, is a 4.5. And phosphoric is more for rust removal, soft drinks, things like that. It's a little bit less aggressive than the carbonic. The bubbles that we see in soft drinks are due to the carbon dioxide, and we link that with the Mentos and Coke that we've talked about. But this carbon dioxide dissolves in the water and it forms carbonic acid. So if you've ever used a SodaStream bottle or machine before, it pumps carbon dioxide basically just to carbonate your water. But if you've ever tasted it, you'll notice it tastes different. It has a distinctly tangy taste to it for carbonated water. It does not taste like normal water. And the reason that it tastes different is because when you dissolve carbon dioxide in water, it forms carbonic acid. And exactly as we said, acid has a distinct taste to it. So you've actually made your water acidic. That hydrochloric acid in your stomach is essential for the digestion. It's part of that chemical digestion. So we talked about this previously. Your teeth are the physical. They'll crush the food down. They'll grind it up. You swallow it down into your stomach, and then your stomach dissolves it and chemically breaks it down so it can absorb all the individual nutrients. The DNA, which we'll do in a later topic, that makes up everything in your body is a form of acid. We call it deoxyribonucleic acid. So DNA, that's what it stands for. This is a picture of a double helix, an example of the DNA. And in the early TED Ed video we saw, he talked about the fact that your DNA is coded up of 4 letters, the A, T, C, G. And they are types of acids. For an acid that's strong enough, it'll corrode the body tissues. This is why we say it burns you. It's actually corroding the tissue on your skin. This is why it actually stings if you get lemon juice in a cup. So you might say, well, yeah, but so does like salt water a little bit, but it's not the same. Salt water is almost a little bit more refreshing. But if you get alcohol or a juice in a cut, it stings because it's actually the acid getting in that's burning your tissue. The outer layer of your skin is quite thick. Takes a long time for something like a lemon juice to burn through it, but when you've got a cut, it's much closer to the nerves, you can feel it burning. It's also the same reason that things like bees and ants hurt, because they actually inject a form of acid when they sting you. It's a formic acid. So ants have that formic acid, which is also why if you squish an ant, it gives off a really distinct smell. That thing you're smelling is actually the formic acid from the ants. The reason that we can eat fruit that contains acids is simply because it's very dilute. It's not strong enough to do any damage to our internal organs. If you drank or ate something that was extremely corrosive, then yes, it would do a lot of damage. It would be a really horrible way to die because it would just burn all of your insides. It would be really nasty. So I said before about a dilute acid. And you may be wondering, well, what do we mean by this dilute and concentrated? Really, dilute just means there is a small amount of what we call a solute in a large amount of solvent. And so for acids, what we're talking about is the solvent is water. So water is a solvent. It's something that things dissolve in. The solute, typically we're talking about the thing that dissolves. So often we would say like sugar in water. Sugar is the solute. Water is the solvent. In acid's case, we would say that acid is the solute and the water is the solvent. So if we are diluting acid, really all we do is we add water to it. So we measure out a very specific amount of water per acid, we mix the two, and it just waters it down. And watering something down is diluting it. A concentrated solution, so a concentrated acid, means it has either a very small or close to no water in it. It is just that pure acid, and that's what makes them really, really strong, because they're not separated by water that's not doing anything. Let's look at bases now. So a base neutralizes or cancels out the effect of an acid, and later we'll see the actual equation for how it does that and what it produces. But in general, it's the thing that cancels out an acid. It neutralizes an acid. For example, if we look at toothpaste, so a lot of toothpaste contain a very weak base, and the point of this is that it's neutralizing the acid that's formed by the plaque bacteria in your teeth. So the bacteria plaque actually create acids, and this is what eats away at your teeth. The basic toothpaste cancels that out to stop it being to stop your teeth being eaten away. A lot of household cleaners contain something called caustic soda. Often you see that for drain cleaners and things. They have very, very strong caustic sodas. Sometimes we use ammonia. And again, this is designed to dissolve, eat away at the grease on a surface that we're trying to clean. So it's actually like eating away at it. So the properties of bases has very special properties, just like the acids did. The pH is greater than 7. They're corrosive, although we often use the term caustic because corrosive sort of suggests more acidic, even though it kind of looks like the exact same effect. To distinguish it, we often say they're caustic. So caustic, corrosive will leave for acids. They have a bitter taste. So remember we said acids were that sort of sour taste? The bases are more of a bitter taste. They have a soapy, slimy feel. So if you've ever touched something like a basic cleaning product, it feels really slippery on your fingers. It feels like you've got soap on your fingers. That's actually that caustic feeling. So that's the feeling of a base on your skin. And as we said, they're neutralized by acids. So if you spill something or if you're burning yourself, you get something caustic on yourself, not the way to go, but you could add an acid to it to neutralize it. Chances are it's better if you get it on yourself, just put water on it, water it down. It's the best way to do it. Let's look at some examples of bases. So sodium hydroxide is a very common one. We often hear about that. That has a pH of 14. So that is extremely basic, extremely caustic. So they use that for soap making, drain cleaner. If you've ever seen at the supermarkets, you can get like a small tub of like small granules, and you basically pour that over your sink drain, add a little bit of water, and you can hear it like fizzing away. It gets really hot, and it just dissolves and eats everything inside your drain to try and unblock it. So that's sodium hydroxide. Then going down, you can have things like a calcium hydroxide, which we use in dental applications for treating wastewater, agriculture. Ammonia, another common one for cleaning products, 11.5, so it's still pretty caustic. We've got magnesium hydroxide, potassium hydroxide, aluminium hydroxide, lots of hydroxides here. So you'll notice a common theme, and we will talk about this later, that hydroxides are a really common base. Anything that has hydroxide in it is a base. This OH thing suggests that it's a base component. And then, very, very common, sodium bicarbonate, or bicarb soda as people call it. It's actually a basic substance, 8.3. So baking soda, we use it in fire extinguishers, antacid medicine. That's its equation. We'll see equations later on, but it is a caustic substance. So a base that is soluble in water is called an alkali. You remember in the pH scale we said you've kind of got acids and bases, or acids and alkalis. Specifically, an alkali is a base that can be dissolved in water. So remember I said when you dilute an acid or a base, you add water to it. That's kind of why we're calling them alkalis, because they can be dissolved in water, or soluble in water as we would say. So dish soap, hand washing soap, washing powder, bleach, all of those things are common alkalis because they can all be dissolved or soluble in water. That's how we wash them away. We dissolve them in water, you rinse your sink, you rinse your hands, etc. The soap comes off. It would be very different if they didn't dissolve. It would be very hard to get rid of them. The reason that they feel soapy, so we said alkalis feel soapy on the skin. The reason they do that is because they turn the oil on your skin into a kind of soap. So I said that we use very strong alkalis to create soap from fats. What these things doing is you have natural oil on your skin. You need it to be there. It's what sort of almost moisturizes your skin naturally. The alkali will actually eat into that oil and it turns it into soap. So it actually feels soapy because your skin is being converted, or the fats on your skin are being converted into like human soap, which is kind of gross. But it feels soapy. Eventually it'll start to burn if you leave it long enough because it burns through the fat, starts eating through your skin. So let's look at teeth. We did hint before about the concept of toothpaste being an alkali, but let's look at this in a little bit more detail. When you eat food, often you get it stuck between your teeth. So you often see, sometimes you catch yourself doing it, your friend, they've got like a piece of celery stuck in your teeth, a bit of chicken, a bit of cake, something like that. It just sits there. The bacteria in your mouth are then going to start to feed on it. So they're almost like the food sitting on a bench is going to start rotting away. It's because the bacteria get to it. The same thing happens in your mouth. The bacteria are going to start eating away. The chemical reactions are going to occur. The bacteria produce very weak acids as a waste product of their eating. So they're consuming your food. They give off small amounts of acid. This acid is then slowly reacting with your teeth to decay it away. It's slowly corroding your teeth. So if we look at the decay equation, in simple sense, we've got sugar. So we always need sugar. The bacteria then consume that sugar and they produce an acid. If we take that acid and you sit it on a healthy tooth, so the bacteria is sitting around your teeth because you're not brushing your teeth very often, you're not flossing, etc., they're just going to slowly sit there and just slowly gnaw away to slowly dissolve your teeth. And that's where we get tooth decay. It's that gradual acid eating into your teeth. And remember that your teeth don't regenerate. So you need to look after them. You need to brush them because these tiny little indents that are going to come from this acid are never going to be healed. So it's progressive. So it can take years and years to develop really bad tooth decay, but it's irreversible other than, putting crowns and fillings and things like that, which we don't really want. So let's look at it. We've got our little food particle stuck between our teeth. The decay is going to start to build in because we've got the bacteria. They're slowly eating away, eating those sugars, producing the acids. The acids are then eating into the side of that tooth there. And the enamel, so your teeth have actually got an enamel coating. You've got your inner tooth and then you've got this enamel coating. And the enamel is one of the hardest substances in the body. It's very, very strong. It's what protects your teeth. It's what makes you able to eat really hard food, chew on candy, all those kinds of things. But the acid can slowly dissolve through them. And then the inside of the tooth is actually made of a much softer substance. That's called dentine, which you think about dentists, dentine, it's all related. If that acid from the bacteria is decaying through the enamel, then once you get to that dentine layer, once you've lost your enamel coating, the teeth can get damaged very, very quickly. So it accelerates the process much more rapidly. So it's really important to protect the enamel coating on your teeth. So how do we get rid of the plaque? Best way is just by brushing them. Brushing your teeth. Gets rid of the food. That's the biggest thing. We want to get rid of the food. So there's physical removal of the food, and there's also those chemicals in the toothbrush that are going to help do it. Toothpaste contains very fine abrasives, not enough that they're going to like sandblast your teeth and wear them down, but very finely powdered chalk that helps to scrape that food away. You could just brush your teeth with water and a toothbrush. And for the sake of what we're trying to do, it would do an okay job, but you're never going to get all the food. So that's why we bring in the toothpaste. Some toothpastes are also slightly basic. So not only are they trying to help clean your teeth, but the basic part, that alkaline component, is designing to also neutralize the acid that those bacteria are producing. So it's one thing to get the food away. It's another we then want to neutralize the acid that's sitting on the enamel coating of your teeth. So just a bit of a joke for you. What time should you visit the dentist? The best time to visit the dentist is at 2:30. So stomach acid. Gastric juice is produced in your stomach, and this is designed to help you digest, break down the food you eat. So it's dissolving it, that very strong acid that we talked about in the last lesson. It consists mainly of a slightly diluted hydrochloric acid, the enzymes pepsin and renin, and a bit of water. And they're the main things that work in your stomach. And as I said earlier, your stomach lining, you've got this mucus, which is kind of gross, but it surrounds your stomach. And that's what actually protects the acid from dissolving through. This mucus is sort of protecting the acid from dissolving through your organ layers. Food and drinks, baking powder, self-raising flour, they all contain baking soda, which we said before is sodium hydrogen carbonate. It is a corrosive substance. We can also have acidic substances, such as this thing called cream of tartar. So I don't know if you're particularly into baking, you may have heard of this. We use this in cooking, certainly to create flavors and things like that, but we're using these acids and bases all the time. In the baking soda case, when it becomes moist, when it gets damp or exposed to water, it reacts with the acid to form carbon dioxide. That carbon dioxide is trapped inside the cake and it expands, just like we saw with Coke and Mentos. When you put that in an oven and you cook the cake, you end up with this rising effect. So like when we talk about with bread rising, that's a little bit different because that's the yeast producing carbon dioxide. But when we bake something like a cake, it's the baking soda producing the carbon dioxide that pushes out, kind of balloons all of the floury components, and then it fixes in that position once it cooks. So that's why we use baking soda in cooking. We are also going to do a quiz on this topic. And from there, you can continue. I will see you next lesson.